Welcome to the advanced probability theory based on the geometrical concepts. So this problem is taken from AMC-10B 2018 problem 22, which means it's hard enough. So real numbers x and y are chosen independently and uniformly at random from the interval from 0 to 1. Which of the following numbers is closest to the probability that x, y, and 1 are the side lengths of an obtuse triangle? Okay, so if x and y are taken from interval 0, 1, then 1 should be the longest side of the obtuse triangle. So it looks like this. This is x, this is y, and this is 1. 1 apparently is the longest side. So for the problems like that, where x is uniformly distributed over the interval from 0 to 1, and y is also distributed on the same interval, so we can represent the situation on the xy plane. X, y, x is from 0 to 1, and y is from 0 to 1. So x, y, when you choose a pair x, y, it means you choose a point inside the square with sides 0, 1, 0, 1, as I showed on the diagram. So, and this point is randomly picked in this square. So this makes the problem geometrical, but we have to set up some conditions on x and y. So of course I'll use what is called triangles inequality. Triangles inequality says that the sum of the two sides of a triangle is strictly bigger than the third side. In this case, it's 1. And there is no need to consider other triangles inequalities like x and 1 must be bigger than y. This two sides summed up must be bigger than the third side because it's true due to the fact y is just a number from 0 to 1. Of course, 1 is bigger than that number. So of course, bigger than or equal to, but who cares about this particular cases when we're talking about continuous distributions. So we consider only the case where x plus y is bigger than 1. So I have to put this inequality inside the square. So I have to shade the points that satisfy this inequality. So first I start with x plus y is equal to 1. So in order to draw a straight line, I just put 2 points on the xy plane. If x is 0, then y is 1. So it's this red point. If y is 0, then x is 1. It's this point. So I connect these 2 points, and I have to choose between the two halves of the square. So x plus y is bigger than 1, so it must be the upper side. So you can choose a sample point to make sure this point satisfies this inequality, and all other points from the semiplane, so they also satisfy the inequality. So I can shade it like this. So this is the triangles inequality. The first condition I put. So it's x plus y is bigger than 1. But it's not the only condition that x and y must satisfy in order to be sides of an obtuse angled triangle. So I understand this angle between x and y as an obtuse angle. Let's say it's alpha. Then I can write a cosine rule: x squared plus y squared minus 2 times x times y times cosine of angle alpha must be equal to 1 squared. That is 1. So this is the famous cosine rule. But cosine of an obtuse angle, cosine of alpha, is negative number. It's a negative number. I don't know this number exactly, but it's a negative number. So if cosine of alpha is a negative number, along with this negative sign in front of it, we have a positive expression here. It's a positive expression. So it's a positive expression that can be moved to the other side, which means x squared plus y squared is 1 minus something positive. That makes x squared plus y squared less than 1. Less than 1. So I have to put this condition in the xy plane as well. And I recognize a circle centered at the origin with the radius of 1. This is the origin. Let me use green color. So this is the origin. And radius of 1 means I have to put my xy point with coordinates of x and y inside the circle. So that is, it must be here. So there are two conditions. So there are two conditions. My point must be inside the circle, in the first quadrant, of course, inside the circle, but also x and y must satisfy the triangles inequality. That is, it must be in the red region as well. So of course, these two conditions must be fulfilled at the same time, simultaneously. That is, this is the preferred region. The randomly chosen point must lie inside. So I have to find this area A and divide it by the whole area of 1. So the area of the square, it's 1. So I have to find this area. Of course, it's a sector. It's a green sector. It's area of the sector minus area of the triangle. Area of this triangle. So area of the sector is pi r square. R is 1 for the circle region. Its area, its radius is 1. Pi r squared divided by 4, because I take only a quarter of the circle. Pi r squared over 4. It's sector minus triangle. So triangle is a right angle triangle. So its area is a half times the product of two legs, 1 and 1. So it's pi over 4 minus 1/2. This is the area of A. So it's preferred region. And we divide this area by the area of the big square. It's 1. So now I have to approximate the area. Pi is 3.14. When I divide it by 4, by 4, it's 0.78 probably, minus 0.5, so it's 0.28. Very close to 0.28, maybe 0.29. So the closest number is C, 0.29. So this is an advanced technique. It uses geometrical concepts of probability, but in order to use them, you have to first find the conditions. This is the first condition. It's triangles inequality. And this is the second condition. It's cosine rule. That's it. So it's a good problem from AMC. I hope you enjoyed it. So see you next time in the next video.